Welcome back. You ready to get started on the third exam, content? All right. So first I'm going to highlight some of the resources that are available to start you getting ready for and prepared and confident in the mastery exam that's going to be coming up next week, next Wednesday. So I added this little module here, Mastery Test Preparation Resources. None of these resources are new. They're all from the ASU MAT265 page. They were created by one of the course coordinators who also creates the mastery test. So they're this sort of stuff here. There's this first one, he calls it Math. He set up his own website called Math Shower. It's got resources on taking a derivative. So there's, like, you look at the chain, well, let's just take a look. You click on here, you can meet him. I've worked with him for probably close to 20 years because he's also worked at the community college at Scottsdale Community College, so I've known him for quite a while. But say you have trouble with, I don't know, chain rule. So he's got a section here on chain rule. He's got a video that will kind of walk you through. And then he's got some games. You can do single-player games, multiplayer games, kind of make it a little fun of taking derivatives. Okay, so those are here for any type of thing that you might want to get some more practice with or something that you're struggling with. Once you're feeling good about taking derivatives, he's also got a similar thing, but it's a lot like the mastery test itself. Once you start it, it's time to kind of give you the feel. It's 50 minutes, which is how long we have in class to take the mastery test. So that's, so it's got the same amount of time on it. And it's set up just really like the mastery test, except the cool part is, unlike the mastery test, you'll be able to find out whether you got the answer right or wrong. So they give you a function to take the derivative of. They give you 4 choices, which that's what the mastery test is, multiple choice. You just have to choose the right one. I'll just randomly do it. If you don't, it tells you that you're wrong, so then it lets you try another one. Oh, I got it right, but I was just guessing, so maybe I want to figure out why I got it right. So again, you can, and the timer's going, so you can kind of go through these and keep going. Notice I got minus 20 because every time you guess, you lose some points, and so it kind of gives you that feel. But you can go through it this way. What it is showing you that you can kind of take a look and maybe you can recognize them. It's got a lot of different functions in here. And I don't know if they refresh. I think when I was doing this earlier, and I'm just clicking. Oh, now I'm right. So see, now I'm down to negative 40. But you can go through and practice. Again, it's set up really just like the mastery test. That's all the mastery test is. Here's a function, take its derivative, choose the answer for the right derivative. Okay. And then for those of you who maybe prefer paper and pencil type things, there's a PDF version with just a bunch to take derivatives of. You don't do the multiple choice. There's the correct answer is on the last sheets. So that's there as well. So you can pull that one up and you'll see it's a PDF with I think about 40 different functions to take derivatives of. The mastery test only has 20. So multiple ways to practice and get ready for that. The content we're going to keep working on through till Friday is all about taking derivatives and applications of it. So it will also be helpful to you because we're going to be taking derivatives. There's just nothing new. After we finish the mastery test, then we start working on what we call anti-derivatives. We start to get into integration, which is the opposite, or going the other direction. Okay. So those are the resources available. I encourage you to start looking through them, working on them. You don't have to use them all. You can use what works for you. And that's right there on our modules. We're here today in the mean value theorem. Does anyone remember we had something called the intermediate value theorem? that if you had two endpoints, that you were guaranteed there would be somewhere you take on a value in between them, right? Because if you're going to go from here to here, you've got to connect it. So that's kind of what the mean value theorem's doing, but it's going to apply to the derivative. So we'll take a look at that, and we'll be all set for today. If you were not here on Friday, I still had, by good luck, I still have the exams with me, so if you didn't pick up your exam, please come by at the end of class and I'll get that to you. Okay. Any questions about where we're going or where we've been? Because I'll show you where we're going in just a moment. So we're going to talk about the mean value theorem. A mean in statistics means average. So what this is really about is that sort of if you've got two endpoints, that you're guaranteed that you will take on the average value somewhere in there. So the average value, average rate of change, is a slope between those 2 points. And we're guaranteed that somewhere in between this function that is continuous between those 2 points, there will be another point that has the same rate of change. Okay. So one thing I wanted to highlight is I made a slight adjustment to our schedule. So we are here today. We've got 4.4, which is, I can't remember now, but it's another thing involving derivatives. We will review for the mastery test, so we'll do a day of some practice. If you're wanting to practice on your own, that's fine. But give you that sort of day where you don't have any new content coming at you before the mastery test. So you can do really well in the mastery test. This Friday, I have a conference I'm going to. And so as we're going to, what I did is I removed the Chapter 4 review date from this Wednesday. I moved 4.5 and 4.7. 4.5 is using derivatives to optimize things, and it's a pretty heavy-duty section. Okay, so we're going to give you some time after taking the mastery test. That Friday will be an online component. And what am I going to do? I'll review 4.1 to 4.4. So you'll still get the review, but it'll be a video review. You can kind of just chill out after doing the mastery test. I'll get your results up there, and then come back ready on 4.5. We're still going to be using the derivative, but we're going to be applying it to more engineering type questions to maximize or to minimize something. 4.7 is where we do the antiderivative, which is doing the derivative backwards, and that's going to open up the door to integration, okay, which is the last part of this class. And again, it's just really doing what we've been doing, but doing it backwards, which sometimes is a little difficult. Sometimes it's easier to do things backwards for some of us anyway. And then after the third test, well, we've got 2 more sections in 5, Chapter 3, our third test, and then we've got 2 sections, and then we've got our final. So I know some of you, I've gotten emails about how can I improve my grade and such. Remember, whatever, so far we've had 2 exams, the lowest one will get dropped and replaced by the final. So the best thing to do is to stick on with the track we're going, to do well, score well on that final exam. That'll replace at least one of the exams. What's that? Well, then that's not really a good, then you keep the other ones, and yeah, we won't replace a higher score with a lower score, but just for those who've got lower scores, that final will be there. Final is sort of the biggest part, and it's really everything, so hopefully by then your final is your highest score. That's our goal. Do well on the mastery test, even though it only counts half of a test. If you do well on that, that's a nice thing. Do well on the third test, do well on the final, and all of a sudden, whatever that first or second test, whichever one was the lowest, is replaced by that, and you'll be in good shape. Okay. All right. So first, before we start talking about the mean value theorem, which again is just saying that you've got 2 points, you've got an average rate of change connecting those 2 points, that we're guaranteed to find a sort of a point in between on the function that has that same rate of change. So there's going to be some place where the tangent line is parallel to that. But before we get there, we do something called Rolle's theorem, which we actually don't use in the homework. We could probably have skipped it, but if you're going to do a proof of the mean value theorem, you need Rolle's theorem to kind of get you that first step. So we'll talk about a little bit. So first of all, Rolle's theorem, you have to have a function that is continuous on the closed interval between 2 points, A and B, so that includes the endpoints. It has to be able to be differentiable on the open interval, so that's not including the endpoints, because you can't take a derivative at an endpoint, remember, because there's an infinite number of lines that can go through a point. So if those two if those two things are met, what this is telling us is that, sorry, one more thing that has to happen. F of A has to be equal to F of B, so the y values for those 2 points have to be the same. So that means that there's a horizontal line connecting them. So this is kind of the easier one that, okay, it's saying if you have a slope of 0, and you be somewhere between these 2 points, since you have to go up and come back down, you're guaranteed to get another place where you have a slope of 0. Does that kind of make sense? What this is saying, we've got some sort of continuous function between A and B, and notice A and B are horizontal, or they're on a horizontal line. That means that they're equal, their outputs are equal, and that whatever this function is, you're guaranteed, because it's continuous, to have at least one point where you will also have a horizontal, the derivative will be 0, right? That's what this says. And that turns out not to be too hard to prove, because you've got A and B just kind of fixed there. What the mean value theorem does is it takes away step number 3. A and B don't have to be equal, so they can be off like this. And now it's a little bit, we've got to show a lot of different cases because we've moved it. Okay, but if the Rolle's theorem works, why wouldn't the other one work? Okay, and again, this is not a mathematical proofs course, so we're not going to go through that heavy-duty proof, but I'm going to show you using Desmo sort of a visual proof that does work in a way that you could check it for any one that you do. Okay, so that was Rolle's theorem. The mean value theorem is saying that we aren't limited to having the output of A equal to the output of B. It doesn't have to be a horizontal line. It's simply saying the first 2 steps has to be continuous, have to be able to take the derivative on that interval, and basically it's saying that the derivative at some point will be equal to the average rate of change. And this again really is y2 minus y1 over x2 minus x1. So it's the slope formula. So those are the slope between A and B, the first point and the second point. So, and we'll take a look at what that does. Again, they also show algebraically, if you wanted to, you could multiply both sides by A minus B, and you can have the formula a little different depending upon what we need to do. And we're going to use both of these 2 in the homework. The second part we just use really once in the homework. And I've got just 2 examples. One we're going to kind of go detail through. We're going to do it graphically so we kind of see how this works. We'll also do it analytically, so you'll see how that works as well. Okay, so far any questions? We doing okay? Okay, and again, in the book it does go through a proof of that these things work, and that's why you need Rolle's theorem, because once you prove that, then the mean value theorem just says refer back to that and goes from there, and then looks at some special cases. So what does this look like? I don't remember. There's one way. So we've got 2 points, A and B, and again, there could be just like that. Since it's continuous, you have to go from A to B, and it might be up or it might be down, but you're guaranteed that somewhere along there, and that's not a maximum, but somewhere along there you'll get a tangent line that's parallel to the line connecting A and B. A and B, that line, its slope is the average rate of change of the whole function. The other blue function line up there that's parallel has that same slope. It's coming from the derivative. And it will occur at least at one point, but it could occur at more than one point, such as this one. You go up and down. So there could be more than one place that it happens. I guess in the case of a straight line, it would occur everywhere, right? If you got a straight line, they've all got the same slope. But it's an existence theorem. So it says it does exist. So if if you're traveling from A to B, and you know what your average rate of change is, you know that was at some point in that travel, if your average rate of change was 60 miles per hour, somewhere in that trip you were going exactly 60 miles an hour. I suppose you could use it if you got a ticket somewhere. You could say, well, my average rate of change and using the mean value theorem means I couldn't have been going 120, because I don't know if you could prove that, but give it a try. Okay, so here's the first example we're going to take a look at. Remember, there's only going to be one more, so this will be pretty quick, because this is really all we have to do. Is you're going to take a derivative, right, because that's what we're going to prove, and we're going to plug in some values, so most of this is going to be algebraic. So we've been asked to use the mean value theorem. We're given a function. We want to find the average rate of change, and then we want to find the value of c that makes that the function, the derivative, equal to the ARC, which is average rate of change. Throw something in there. So I think I'd like to do this one, if I can remember how all the steps I took, using, let's keep what we got, using Desmos. Okay, so we've got a function, f of x equals, what was it? Was 4x cubed plus 2x?
Plus 2x squared.
2x squared plus x. Okay, thank you. Plus 2x squared plus x minus 5. So there's our function. Oops. Let's see. Go out a little bit. So I'm just going to show you kind of a cool way using Desmos that I figured I could use this. We want to find between -1 and 1. And I chose those points because they're actually fairly easy, plugging in -1 and 1. So you might not need to do it this way, but I want to plot the point -1, f of -1. And what we see, oops, I haven't plotted it yet. Oh yes, I have. So it plotted it right down here. So if I click on that, I see when I plug in -1, I'll get -8. I guess I could have plugged in -1 and calculated it, but Desmos did it for me. And because I want you to be able to see the visual, we also want the point 1, f of 1. Oops. So we'll plot that one. I will make them both blue. Okay, and so what we're doing now is we want to find, we've got our 2 points. We want the average rate of change. I suppose we could calculate that. So first of all, we need our 2 points. So -1, -8, 1, 2. I'll just do my work here. And we had 1, 2. So first we go about finding the slope. So that's 2 subtract -8, right? y2 minus y1 over x2 minus x1. 2 subtract, so that's a pot. 2 plus 8 gives us 10. 1 plus 1 gives us 2. So we have our slope is going to be 5. So that's the average rate of change if we were to put a line between here and here, it would have a slope of 5. I'm actually wanting to plot that line, so we need to find the y-intercept. So let's do that. So y equals 5x plus b. Let's plug in this point here, 1 and 2. So I plug in 1 for x, and we're going to get 2 for y. Gives us b. So we get 2 equals 5 plus b. Subtract 5 from both sides, and we get that b equals -3. So our line that connects the two, our secant line, right? These 2 points is going to be y equals 5x minus 3. Okay, so we've done that part. And what the theorem is telling us is that there's some other place on this graph that will have the derivative will be 5. And I want to show you both ways. So let me just clear this out. Delete all that. Let's put this graph in here. Let's graph the line y equals 5x minus 3. And yes, indeed, it does cross. It does connect these 2 points here, 1, 2, and -1, 8. So we see that. Can you see where a parallel line would basically be the tangent line to this function here? I'm going to do it with, I know that that tangent line has to have what kind of a slope? Has to be 5x. It will probably have a different y-intercept, so I'm going to do plus b, and I'm going to do b as a slider. And what I'm going to be able to do now is I can slide, oh look, you can kind of visually see if I slide that over, changing the y-intercept, that now those two, we know those 2 lines are parallel, right? Because they have the same slope. Can you see that that's sort of a proof that there is a point where this happens? Of course, this doesn't necessarily help us find exactly where that intersection is. We'll go back and do it analytically, but hopefully visually. And let me, I think what might help is, let's bring the window in a little bit. Let's go -5 to 5. So we can still see it, but we're kind of squished in a little bit. And then it doesn't look quite like it's touching, but you could see if I, yeah, maybe about there. And so what I'm going to do is I'm going to click here. I can see it's about there. So I'm expecting a value about 0.444 when x is 0.444. The derivative should be 5, right about there. So I've got an estimate. Again, it's a rough estimate because it could be anywhere in here because it's not really showing me that they've intersected. Although, I think, yeah, see if I go a little bit more, I've actually got 2 places of intersection. So I played with this a little bit. I could go maybe 6.1, and that gets me a little bit better estimate. But what we'll do is we'll just, about 0.45. So let's kind of go back here. We found the average rate of change. Oops, let's go back. We found that to be equal to 5, and we even went a little bit further and got the secant line. You know, that's good for us. Now we want to show that the derivative is equal to 5 at some point. So what we're going to need is, we're going to need this derivative. So 3 times 4 is 12, x squared, subtract 1 from the exponent. The next term, we get 2 times 2 is going to give us 4, x to the first power. Take the derivative of x to the first, and we get 1, x to the 0, which is 1. And we take derivative of -5, we get 0. So this is our derivative. And what we're going to do is we're going to say that somewhere, there is some point where this derivative, some x value, where x will be equal to 5. And again, from our visual, we expect it to be some number, maybe about 0.45 or something in there, right? Ballpark. How do we solve this? It's a quadratic. Let's get it equal to 0 and then see if we can factor it. If not, we would use the quadratic formula, or we could graph it and see where it crosses. There's a number of different ways to do it, but now it's all algebra, right? We've done the calculus step. We took the derivative. Now it's algebra, finding what value of x makes this function equal 5. So I'm going to go ahead and subtract 5 from both sides. And I get 12x squared plus 4x minus 4 is equal to 0. I can factor out a 4 from each of these, right? Wait a minute. Did I get that right? I think I did.
Yeah.
It didn't work out exactly how, so I manipulated to get it to work how I wanted it to work, but then I might have messed up when I was doing that. Well, we'll see. So we could factor out a 4, so then we have 0 equals 4. 3x squared plus 4. No, the 4 has been factored out. Minus 1. Okay. So we could divide both sides by 4, so that, the 4 just goes away. Let's see if we can factor this. If it factors, it'll probably be 3x minus 1 and x plus 1. I must have gotten something wrong. It was supposed to become like an integer value. It's not factoring. That's not going to factor, is it? Well, all that time spent doing that. So, but we could use the quadratic formula. We could also solve this graphically. I could just take 3x squared plus x minus 1, graph it, and see where it crosses the x-axis, right? So let's open up a new Desmos, because I want to come back to that other one. So what was our derivative? It was 3x squared plus x minus 1. And I find 2 places. Doesn't that number kind of look familiar? 4.34. That's about where it was. And then what I want to do is I want to go back there, put that in there, and show that that is the place where it'll do it. There's a second one over here. I think that's still in our domain, isn't it? Because we're going from -1 to 1. So the cool part of doing this is I now find I'd probably have 2 solutions, right? Remember, existence says there is at least 1, but there could be more than 1. So let's note these down. We'll go back to our original graph and we'll see if we get that to happen at both places. So 4.434. So let's do this. What can I take away? Let me take, yeah, actually, the way it's going, right, if I come back here, that looks like the other place over here that I didn't even think to look at. So there's our other solution. So there's actually 2 solutions, and graphically I didn't look at it close enough to see that there could be 2. But now it shows it. That's the beauty of going with this. So what I'm going to do is, let me go ahead and take this one out. We'll leave this line in. What we're going to do is we're going to graph the derivative. Call it g of x. And since we found it, it's going to be 12x squared plus 4x plus 1. And what we're going to see is when we plug in, now it might not look like how's that going to match up here, but what we found is if, what was the function? It was g of, it was a 0.434. 434. Notice I get pretty close to 5 there, little within a rounding here, right? I get 4.996. Okay. So that's, you know, just showing that the derivative function for over here, we would have that line. We could actually plug it in. The other one I could plug in is my negative 0.768. And we find it also has a slope of 5, or a value of 5. Remember, this is the derivative at that point. And again, you could have analytically taken the derivative, plugged those in for x, and you would have found it. Okay. But notice to actually solve for them, we had to use our quadratic techniques. We have to either use the quadratic formula or go for it graphically. Personally, I like the graphically. Or if it factors, we could factor it. Graphically will always work. Quadratic formula will always work, but it's a pain if you get it right. But it just shows us we've got these two places. Of course, we would, and again, we did have that line where we could see visually the slope of tangent lines at about those points were parallel to the average rate of change. That's the mean value theorem. It just says that it will exist. Okay? So if you do know the average, you know that somewhere in that process, as long as it's continuous, as long as it's differentiable, that you are guaranteed to get that average rate of change somewhere in the middle, somewhere between them. And your homework is taking a bunch of functions like this, doing the same thing. A number of them, they will tell you that there is only one place where that such point occurs, so that makes it a little easier. But again, you could do it with the graphing, you can do it analytically. But let me take a look at this one. There's a homework problem similar to this, and this kind of uses the second form of the mean value theorem. And I just wanted to help you kind of think through this. So we've got some function, g of x, which is continuous on this closed interval, 3 to 7. That's one of the requirements. And then we're just told that the derivative of g is, for any x, it's between -4 and 5. So this is kind of backwards. We don't know what the average rate of change is, but we are telling, because the mean value theorem works both ways. It's also telling us if we have, if we know the boundaries of the derivative, we know that the average rate of change has to be within that range as well, because it can't be, the average rate of change couldn't be -5 because there's no point that has a derivative of -5. So then that would blow the mean value theorem. Okay, so but the way we go about doing this is we're going to try to estimate this right here. And notice that's the top part of the fraction, right? That's the top part of the average rate of change. What would be the bottom of the average rate of change? 7 minus 3. Okay, so what we're looking at is that we've got g of 7. And this would be the average rate of change. So we've got that g of 7 minus g of 3 divided by 4, right? 7 minus 3 is 4. This has to be less than 5, but greater than -4, because that's all that we're told that that's all the derivative does. It takes on all those values in between. So how do we solve this one? Multiply all parts by 4, right? Because that's where really they're saying estimate what this top part could be, the difference between the two y values. So we multiply everything by 4, 4, and 4. Again, this is all just algebra. So 4 times 4 is 16, so we get negative 16. 4 divided by 4 cancels out. We get that g of 7 minus g of 3. Oops, not equal to. Unless the problem gave us that they were equal to. It could be. And then we have 4 times 5 is 20. So what it did allow us to do is narrow down that the difference between the y values is somewhere between negative 16 and 20. Now that's not maybe that's still a fairly wide range of things, but it gives us at least some boundaries. So again, if we were designing something, this is something we've got something that has an average rate of change, and we know what the average rate of the boundaries for the average rate of change. We know the sort of the limits of what we can do with our endpoints. If we know what our endpoints are, we know what this machine will be able to do. We know a guaranteed rate of change in between there if all these things are met. Okay, so there's one homework problem that's sort of set up like this. You just have to think of the mean value theorem in almost reverse, right? Yes.
Why is G7 minus G3 over 4?
Because it's over 4 because x is 7 and 3, so 7 minus 3 is 4. So remember, the mean value theorem says that the derivative of g at some point has to be equal to the average rate of change. So there's the y values. And then 7 minus 3, so the x values. So that's the average rate of change of the g function from the two endpoints. And the mean value theorem says somewhere in between we will get that. And so if we know the boundaries of what the derivative can be, we know that we can't go either higher or lower than those numbers, because otherwise that would violate the mean value theorem. It's kind of, you gotta think in circles. I'm real good at doing that, but sometimes hard to get out of the circle. But so I wanted you to at least see that, and it's using sort of the mean value theorem in reverse. And I figured this one might be something that kind of gets you to stop unless you kind of at least saw one example of it. Okay, so there's one in the homework that's similar. Take a look at it, but it's just taking that denominator, multiplying everything by the denominator and seeing that you'll be there. The other ones are just pretty straightforward. Here's a function. What is the average rate of change between the two endpoints? You'll do that. So you can, and again, you could use Desmos. You could plug in the values, and then where is the point? What is the c value that we got that same matching average rate of change? We good? Awesome. It's right here. Yeah. So we've estimated always. Yeah, we just estimated between negative 16 and 20. It doesn't seem like a very satisfying answer, but that's what it has to be between them. Okay, so we knew that the slope was 5, right? And so to find the slope of the tangent line, what did I do? Oh, it's not a tangent. To find the slope, to find the actual secant line, 5x, and then I plugged in one of the points. I plugged in 1, 2. I could have plugged in -1 and -8, and I would have got the same
It
answer.
was 2. Okay, I thought it was negative. Okay.
Yeah. Very good. Matthew?
Same issue.
Hayes. Okay. Jackson.
I can take this one.
Yeah, it's all yours.
T-O-H.
There we go.
Yep.
G.U. Lewis.
Thank you.
A.U. W. N.G.
Yeah, yes.
Okay. No, that's okay.
Also, I had a question. When was the homework?
The last, I extended it until Sunday night.
Okay. Mine was graded like
Right, and so that was just an update for the test. I will update again this week, so you'll see another
Thank you.
update. Okay, yeah.
I had a question regarding the mock exam.
Yes.
So for the
last
notes
question
provided, I tried
absolutely
practicing on that.
did?
Like whenever I mark an incorrect answer, it gets negative points.
Right.
So would that be a pass-free exam?
No.
So it's not like
Yeah, so it's just so that if you're guessing around that you don't end, I got 100%. But that's just for the practice.
okay, in the exam it won't be negative.
No. If you miss it, you miss it. So there's 20 points, there must be 5 points each, so you can, yeah,
So
we're not
0
gonna-
for missed questions.
Right,
Okay,
yes. Good question.
Thank you so
Yes.
much.
You too. Oops, I always forget.